in this segment, we're going to prove Gödel's theorem. So let me remind you what the result says as we're understanding it here. So take some rich enough arithmetical language, and I'll tell you in a bit what rich enough means. So different ways of formulating the theorem. On one formulation, what it says is that given our language, it's impossible to program a Turing machine so that it works forever, outputting sentences of L. It eventually outputs every truth, and it never outputs any falsehood of L. So more succinctly, no Turing machine can output just the truths of L. A different equivalent formulation is that no Turing machine could decide the truth of an arbitrarily given sentence of L. So you couldn't construct a Turing machine such that if you give it any sentence of L, it outputs 0 if the sentence is false and 1 if the sentence is true. So there are different ways of setting things up, but here's a way of setting things up where the theorem is especially easy to prove. So let's just define rich enough to mean rich enough for this lemma to be provable. So the lemma says that L is such that you can characterize some formula, which I'm going to abbreviate halt of n, such that for any given n, that formula is true if and only if the nth Turing machine halts on input n. In other words, we're defining rich enough to mean rich enough so that L is able to express the halting function. So let's see how we can now prove the theorem. So let me start with version 2 because it's easier to prove. So suppose not. Suppose we had a Turing machine that can decide truth for L. Then we could use it to compute the halting function. Because if you're given number k and you want to figure out whether the kth Turing machine halts on input k, what you can do is you can just give this Turing machine as input the formula halt k and see if you get a 1 or a 0. And of course, if you can do that, then you can also program a Turing machine that uses this Turing machine's program as a subroutine and does everything itself. So on pain of computing a function that we know not to be computable, no Turing machine could decide truth for L. Let's now prove version 1. It's a very similar idea. Suppose you did have a Turing machine that worked forever, eventually output every sentence of L that's true, and never outputs a sentence that's false. And now suppose you want to know whether the kth Turing machine halts on input k. Then set the machine in motion and wait until it either prints out halt k or not halt k. You know it'll eventually print out one or the other because it prints out every truth eventually, and one of these has got to be true. And when it eventually does output one of these, you can be sure that it's true because it never prints out any falsehoods. So again, if you wanted to use this machine to construct a machine that computes the halting function, you could take the code of this machine as your starting point and then modify it so that it's constantly checking whether the sentence just printed is of one of these forms. And when you get that, it gives you 1 in this case and a 0 in that case. So when we define rich enough in this way, it's totally straightforward to show that Gödel's theorem has to be true. Now, one thing to point out is that as formulated, the theorem is not very interesting unless it turns out that there are interesting languages that satisfy our condition, interesting languages which allow us to prove the lemma. So, for example, if there was no such language, then Gödel's theorem would be true, but trivially so. Or if there were such languages, but they were strange and complex, then it would also be true, but not for very interesting reasons. The reason Gödel's theorem is so interesting and so powerful is that it turns out that this condition is not hard to satisfy at all. In fact, it can be satisfied by the super simple language L, which we characterized earlier. So in the next video, what I'm going to do is I'm going to sketch a procedure for verifying that our super simple language generates this lemma. And any interesting language you can think of will be at least as powerful as L, so it'll follow from that that any interesting language is going to satisfy our lemma and therefore allow for the theorem to be proved.